Here we're going to look at the mean and the variance of a Wilcoxon signed rank test statistic. And a little background, we're in the one sample location model arena, and we have our data. It's a independent, identically distributed, continuous, with this distribution function, and it really should say absolutely continuous. And the Wilcoxon signed rank test, in the last video we did, we showed that it's equivalent to the number of positive Walsh averages. And so you can go back and look at the video for that. Now to find the mean and the variance, remember, it's an arbitrary distribution function, so we technically can't calculate it unless we know that specifically. So we're going to develop some notation generically. We're going to let P1 be the probability that any one of our variables is positive. So X1 is greater than 0. We're going to let P2 be that the sum of these is greater than 0. And P3 is that the sum is greater than 0 and that X1 is greater than 0. And P4 is going to be that this sum and this sum is greater than 0. Notice that the X1 is the same here and the same there. Now in the development of this, it really makes it much more intuitive, much easier to have P1, 2, 3, and 4. But it should be noted that we technically don't need P3 because it can be rewritten as P2 plus P1 squared divided by 2. And maybe that's homework for anyone that wants to try. It's not very tough, but we're not doing that in this video. So the theorem says that the mean of our test statistic here is n P1 plus n minus 1 over 2 P2, and the variance is this expression. Okay, now we're going to go through and prove that. So to develop some further notation is we're going to let Tij be an indicator function, meaning 1 or 0, and it's 1 if the Walsh average is positive, and it's 0 otherwise. And then we note that T, our test statistic, is the sum of these indicator functions. And what this is doing is counting how many Walsh averages are positive. And that is the Wilcoxon signed rank test. It's an equivalent to the original definition. And I said in a previous video, we showed that. So you can go back and look at that. So the expected value of T, so we plug in this here, but expectation is a linear operator, so it goes through the summation signs. And then we treat this with two cases. One where I and J are equal, and then of course one that they're different. So that's what this is. So where they're equal, there's just one sum, and then here the I is less than J. Now to note that T11, now T11 up here, it says that T is that X1 plus X1 over 2, so really that's X1 is greater than 0. So the expectation of T11 is 1 times the probability of observing the 1, which is the probability that X1 is greater than 0. Well, that's this right here, and we call that P1. Now this one, that Tij, so that means that this is it, that xi plus xj over 2 is greater than 0. So this can be multiplied over, so this sum is greater than 0. So this expected value right here is it's the value times the probability of observing that. So it's probability, it's 1 times this probability, which we call T2. So we can put P1 here and P2 here, and then we since there's no index, we take it out front, and then sum, there's n of those, and there's no index here, so it can be out front, and then I less than j, there is n times n minus 1 over 2 of those. So that, well, that's the expected value. Now the covariance, let's we're going to kind of go slow, and you kind of get my way of thinking about this. When we look at the covariance, remember that the t, these are independent observations, I and j. Okay, so when we look at the covariance of T12 and T34, so this one, T12, is independent of 3 and 4, because you know the x1, x2, and x3, x4 have nothing to do with each other. So the covariance is 0. And matter of fact, whenever the index is here, you know, there's not something common over here, it's all 0. So example would be T11 and T22. So those are independent. Or T11 and T23. So I mean, there's a lot of those that where the 2 indexes we choose here are not the same as here. Well, those are all 0. Okay. So now we start thinking of all the possible ways that we can have indexes that are the same when we go back and forth. Okay. So they could all equal. So T11, T11. That's the variance of T11, which is the expected value of T11 squared minus the expectation quantity squared. Well, this now, since it's T is an indicator, it's 1 or 0, so it equals the mean. This is equal to the mean, so and then minus that. Well, the probability, you know, or expected value of T11 is just P1. So which is what we said here. So this is, that's P1, and that's P1 squared. And now another way that we can have common indexes is where these two equal these two. So that to find the variance, it's the expected value of T12 squared minus T12. And since this is an indicator, it's a 0, 1 variable, this is actually equal to the mean. So it's the probability that the sum is greater than 0. So it's P2, and then that's P2 squared. So that's the covariance of those. And then, so there's 2 more cases. Here that they're equal, and one of these is equal to that. And we look at the expected value of this and that minus, you know, this is the definition of covariance. And let's do this part first. That is P1, and this is P2. Now this one, the expected value of T11 and T2, so the values that this combination can take on are 1, 1, 1, 0, 0, 1, and 0, 0. And so the way you take the expected value, take the value times probability of that occurrence happening. But 3 of the 4 is 0, so those don't add up into the sum. Well, the case that we can have both of these equal to 1 is when this is, when, you know, it's the probability that x1 is greater than 0, and here is the probability that x1 plus x2 is greater than 0, which we called P3 on the previous page. And here is the last possible combination. And this, we're doing this before we get into the variance of T. So we could just have the first index the same, and then that expectation ends up being this, where that's P2 and P2. It's the same because the variables are IID. So the probability that x1 plus x2 is greater than 0 is actually the same as the probability that x1 plus x3 is greater than 0. So it's all the same. Now this one is the probability that the sum of x1 plus x2 is greater than 0, and the probability that x1 and x3 is greater than 0, which we called P4 on the previous page. Now one note here is that we're only considering it one way. So technically we could flip these. So we could have the T12 here and the T11 here, but it's the same probability, right? So we're only considering it one way. So technically we could put a 2 here, if we're going to consider them both ways. Same here. And so now let's get into the variance. Now some of these formulas get kind of ugly, and I'm on the back page I go into sort of a much more detail how we get these. But some folks can just look at all these summations, go, oh yeah, well there's n times n minus 1 of those, and it just is obvious to them. But it's not to me, so I have to muscle through it. And I'm going to try to do that here. So we're going to look at the variance of t, which is this. T is defined to be the sum of these Tij's, which is the number of positive Walsh averages. Well, variance is actually just covariance. So this is a sequence of numbers, covariate with the same sequence. But covariance is a linear operator, so these sums can come out and we get this. Okay, so now and some, like this step here that I'm going through, some will go from here to the next step I'm getting ready to show, but to me it's tough. So when you look at the variance of a combination, it's the variance of the individuals and then plus 2 times the covariance of a bunch of junk. So you can do it that way. But here, so we start looking at all the possibles. So remember that these indexes, if the 2 indexes here have nothing to do with the indexes here, you're not the same, then that's 0. So they don't add up into our sum. So we have to find the combinations where there's some commonality here. And so that's this next step. So these are the 4 covariances that we looked at on the previous page, where they're all equal. So that's this sum, where the I and j equals the I and j here. So that's this sum. And then now notice that if we flip them, it's the same. So we don't have to take a times 2. But down here we have II and IL. So if we're only kind of considering this way of thinking about it, and not being able to do the flip back and forth, we just take it times 2, and that's where this 2 comes into play. And then here's the 4th one, where it's IJ and IL. And again, we're technically flip those back and forth, but we're only considering this format, so we'll just take it times 2, and that's this. So then each of these covariances for each I is the same, and same here. So for each IJ combination, it's actually this, we get the same value for each of those. So I'm going to plug in those values here. So this covariance we calculated on previous pages, that this was this, and these were these right here. So then there's no indexes here, and so we can pull them out front, and then we got to figure out, well, how many are we adding up? In the same way here, that could come out front, but how many of them are there? And then this can come out front, but then, and so it's the same game that we have to play. So now I'm going to show you the answer, and then on the next page I'm going to go in very fine detail how to do it. So here there's n of them, and this one there's n times n minus 1 over 2. And here there's actually, if we just look at this, there's n times n minus 1 ways, but then the times 2. And we get that. And then here, there's actually n times n minus 1 times n minus 2 over 2. But then that 2 will come in and cancel the 2 and we get this, okay? So it is true, it is the answer. And for those that go, oh yeah, it's obvious, well, you can turn off the video and be done. But for those of us, including myself, needed this back page, okay? And so, and again, you kind of get the way I'm thinking about it. Here we're going to look at the covariance of T and T. And remember, T is this sum. So we have, now I put the equals out here, the T11, T22 up to TNN. So all of these, you know, have to follow the I strictly less than J. So this is T12, T13 up to T1N. And then this is T23 up to TN and etc. all the way to N minus 1 times N. And now the covariance, remember when we take the covariance, we take the covariance of this times itself, and that's part of one of the variances that we looked at. This times that, you know, this and that covariance, this, and then we just we do them all. Then we start at this one, and we start over. We take the covariance of this and that, the covariance of this and this, this, and we do that for each of them. But notice that we just counted that twice. Initially, I went covariance of this and this, and then went through them all, and then coming around, I went the covariance of this and this, so we did it twice. So that's where that little 2 comes in, because there's no need to do it twice when you already do it once. Okay, so now, when we have this format, now, how many ways can we pick it where the indexes are equal? So it's only these right here. So we can there's n ways to choose equal indexes. And then once this is chosen, how many ways is there to choose that? Well, there's only one way. So there's n ways to have this covariance match this format. Okay. So then the next covariance, we have IJ and IJ. So of these, how many ways can we pick 2 different indexes? Remember, I goes from 1 to n, j goes from 1 to n. Well, that's n choose 2, which is n times n minus 1 over 2. And then once this is picked, there's only one way to pick this one. So there's a total of this many ways. And if you look at the formula in the back, that's what this is, because there was that many ways to pick it. So then the third method is II and IL. So how many ways can we pick II equal? So in this sum, well, there's n of them that are equal. And then once we pick this, how many ways can we pick another index is not equal to I? Well, there's n minus 1. So there's n times n minus 1 ways that we can have this format. And that's what this is, okay? But remember the 2 out front, which was here, right? And that's because we didn't consider the flip-flop of this. We only considered this format. And the last one is IJ and IL. So there's n choose 2 ways to pick 2 different indexes. But then once this is picked, then there's only n minus 2 ways to pick another one that's not one of these. So that means there are this times that ways to pick it. And then, so on the last page, that here, that 2 canceled with the 2 in the denominator and just leaves this. So anyway, we are finished. We found the mean and the variance of of the Wilcoxon sign rank test statistic. I try to go into every little step so nothing can be misunderstood, and hopefully that's not too monotonous for people. Hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.